Our rational functions, however, are going to look like this. So the reason why I don't have a general form like I did last time is because the numerator and the denominator are both going to be polynomials. What the polynomials are is going to change. It could be a binomial with only two terms. It could be a trinomial, like a quadratic function. You can have a monomial. It really just changes. So this is the best way that we can represent that. And it goes on to say that px and qx are polynomials. So you can see on just underneath this box, you can see a bunch of examples. So this one. Any fraction that has a polynomial top and bottom is called a rational function. So we're going to be learning how to do the same kind of things that we did last time, about the horizontal asymptotes, vertical asymptotes, the domain. We're not going to focus on the range for this one because it's a little bit too complicated. But it's going to be the same kind of thing. So it's going to be more complicated. So everybody has this. At least I hope you do. I passed it out as class was starting. This little handout is what's in this box right here, but in a little bit more detail. So you can use this as we're going through the lesson, but if you would like to use this as a reference too, so you don't have to keep flipping back in your notes. This is just a repeat of this information, the step-by-step process that we're going to follow, but in a little bit more detail. So that handout is for you, so you can use that to be more successful as you're working. Before we actually jump right into the information that is the body of this lesson, I want to review continuous versus discontinuous one more time. So I mentioned this before. A continuous graph is an uninterrupted curve or line. So I drew a couple of pictures for you. If you were to draw just a linear function, right, just one stroke of your pencil, we have our cubic function. There are no breaks or interruptions, right? It's just one swoop, right? A discontinuous graph is like what we were talking about last time with the hyperbola, where you have the asymptotes are breaks, so you have two separate parts. Discontinuous, there's a break or a gap. That's our discontinuous type of graph. We're going to be continuing with that, so our graphs are still going to be discontinuous for this lesson. They're just not going to look quite like what they did last lesson. So I want to make sure you guys are aware there are two different types of discontinuities. The one that we've talked about so far, the asymptotes, is listed right here. Now I did mention in the definition of asymptote that it's a line that a graph approaches but doesn't cross. So it's always true for a vertical asymptote. Oops, underline cannot cross through. A vertical asymptote, you will never actually be able to cross or touch it. The reason why we're not going to talk about the range in this lesson is because there are very rare circumstances where you guys can cross the horizontal asymptote. So we don't consider a horizontal asymptote to be a discontinuity because there are some times where you can cross through it. You don't really care. It's there, but it doesn't keep you from going. But for a vertical asymptote, you can never cross it. So, a vertical asymptote is one of our discontinuities. It is called a non-removable discontinuity. This is an important distinction you guys need to make sure you remember. So an asymptote, non-removable discontinuity. Something we haven't talked about yet is called a hole or a point of discontinuity. This is a removable discontinuity. The reason why it's removable, the way that a hole works is it's a point, a single point, that is excluded from your graph. So it's like a little black hole. It's like a little dot that you have to jump over in your graph and continue on forever. So this is another type of discontinuity that's called a removable discontinuity. Okay, so we have our vertical asymptotes and our points or holes of discontinuity. Alright, so that's the first thing I need to make sure you guys are aware of. There are two different types. One's removable and one's not removable. Okay, that's the first thing. Make sure you guys remember that. Now, with that under our belt, we're going to jump into our first example. So I'm just going to go through this list here first before we actually do the example. So this is the list that we're going to follow, and it's also on your handout. The very first thing that you guys need to do is find the horizontal asymptote. Always, every single time. It's the first thing you do. And the way that you find the horizontal asymptote is by looking at the degrees. Do you guys remember what degrees are? We talked about that in Unit 4. Do you guys remember what a degree is? The degree of a polynomial? Just any random exponent? The highest one, right? So what you're going to do is you're going to find the degree without changing anything about the equation itself. It will be changed at some point, sometimes. But before you do anything to this function, the first thing you want to do is find what the degree is on the top and the degree on the bottom. And then we're going to have three different scenarios. If it's bottom heavy, which means that the degree on the bottom is bigger, your horizontal asymptote will always be y equals 0. Always. If it's bottom heavy. If the degrees are the same, the way you're going to find the horizontal asymptote is by taking the two leading coefficients of the top and the bottom and writing them as a fraction. So So if they're equal, you're going to write a fraction, or it could turn out to be a whole number, but you're going to use the leading coefficients. If it's top heavy, so the degree is higher on the top, you are not going to have a horizontal asymptote at all. So I warned you guys, there's a lot of information in this lesson, and you have to memorize it all. So that's the first thing you guys need to do is memorize these 3 possibilities. Bottom heavy, equal, top heavy, they each have their own little scenario here. So let's try that for this example over here. What is the degree, what's the highest exponent on the top? A 1. And what's the highest exponent, sorry, what's the degree of the highest exponent on the bottom? Okay, so the degrees are the same. So you're going to look back over here. If the degrees are the same, top and bottom, that means you are going to write the leading, you're going to take the 2 leading coefficients, write them as a fraction, and that is going to be your horizontal asymptote. What was the leading coefficient of over here? 1. A 1, and the leading coefficient down here? 3. Remember, the leading coefficient is just the very first number right here. That's the standard form. So I'm going to write y equals 1 over 3. And that's how you find your horizontal asymptote. It's one of these 3 scenarios. Because the degrees were the same, I just used the numbers in the very front, the leading coefficients, and I write them as a fraction. Make sure you guys remember an asymptote is a line, so never just give me 1/3. That's not an answer. It needs to be an equation of a line, so y equals 1/3, because it's a horizontal line. Alright, so that is step 1. You don't do anything to the function itself, you just look at the degrees, don't change anything, you just look at the degrees, pick which one of these 3 it is, and then you're done. Now before you can do anything else, what you have to do next is try to factor or simplify. So horizontal asymptote first, and then you try to see if you can factor or simplify anything, because if that happens, it's going to define what happens to the rest of the process. So if I look over here, can I factor x plus 7? No. Can I factor 3x minus 1? No. So if you can't factor anything, that's fine. You're just going to circle this and move on. If you can factor something, which you'll see in a little bit, you would have to factor, you might have to cancel things and simplify it. That's very important to know what you're going to be using in order to move forward. But because nothing can be factored or simplified, we're just going to move on. The vertical asymptote. I'm going to take you guys back to last lesson. When we were here, where did you look to find the vertical asymptote? Which one? H. Where is that in the fraction? The bottom, the denominator, right? The reason why, I don't remember if you guys recall, but at the very beginning of that lesson I said, the reason why we have that vertical asymptote is because h can't be x. If you do x minus x or h minus h, you get 0. Can you divide by 0? No? That's why a vertical asymptote exists. Because it tells you what x value in the denominator would make you divide by 0, which is not possible. That idea carries on to this lesson. To find the vertical asymptote, you're going to look in the denominator. The vertical asymptote always comes from the denominator because it's going to give you what number is not allowed to be in the denominator because you can't divide by 0. So what you're going to do is you're going to look at your denominator, you're going to set each factor in the denominator equal to 0 and solve for x. Very simple. So what's the denominator of my fraction over here? 3x minus 1 is the entire denominator. You want to set that entire thing equal to 0 and solve. Probably do that in your head. You add the 1 divided by 3, I get 1/3. So my vertical asymptote is x equals 1/3. And you can check that. If I plug in 1/3 right here, 3 times 1/3 is 1, 1 minus 1 is 0, you can't divide by 0. That's why 1/3 is an excluded or restricted value. That's why it's our vertical asymptote. Alright, so next thing you would check is to see if there's a hole. The only way that you guys would have a hole on your graph is if you cancel something. So if you didn't cancel anything, if you didn't factor and cancel anything, then you don't have a hole. So this one you can just say does not exist, or you can say none. There isn't one. The only situation in which you would have a hole is if you factored, and you see that you have something in common top bottom and you cancel it out. But that's not happening here. So you can say none or does not exist or something like that. Alright, so after you've checked for your 2 discontinuities, you do horizontal asymptote first, then you see if you can neaten up your function, you look for your discontinuities. The next thing you're going to do is look for your domain. So in your domain, there are 2 things that could potentially interrupt your domain. Just like we saw in our last lesson, the vertical asymptote. The vertical asymptote is an x value that you're excluding, so obviously you have to jump over that in your domain. Another thing that could interrupt your domain is the hole. The x value of the hole is another value of x that isn't allowed in your domain, so there could potentially be a double jump. In this scenario, we don't have a hole, so we only have one number. So what is the number that is not allowed to be in the domain? 1/3, because that's an asymptote. We're going to draw a little dotted line that means that it's not included in the graph. So the domain is exactly the same as what you guys did last time. Whatever your asymptote was, you're going to jump right over it, and you're going to write it using this notation just like we did before. Okay, so nothing new in terms of the domain yet. We'll see something a little bit different happen in a little bit. Right? I know you guys probably have range in there, but you're going to cross it off. We are not worrying about range at all in this lesson. Range gets super complicated for a lot of these graphs because sometimes you cross the horizontal asymptote, sometimes there's an extra gap between the y or x intercept and the horizontal asymptote. It's too complicated. So they won't even ask you to do it in pre-calculus. So if they're not asking you pre-calculus, they're not asking you in algebra 2. So we're only focusing on domain. Range is a non-issue for this type of graph. You have to do the range for the reciprocal functions. For this type, you cannot. Okay, so just focus on domain. Next up are our intercepts. So new, this is new. I didn't ask you to find the x or y intercepts for the previous graphs, but I am going to ask you for these. So to find the x-intercept, that is going to come from the numerator. The denominator gave you the vertical asymptotes. The numerator is going to give you the x-intercepts. So if you guys look at our example here, what's in the numerator of our expression? You're going to take the numerator. You could have multiple things in the numerator. So however many factors you have in the numerator, you're going to set each of them equal to 0, and you're going to solve for x. What would you get for x? How would you write that as an x-intercept? -7. Very simple. So whatever's in the numerator, set equal to 0. You get 1, 2, 3, however many x-intercepts. As you'll have as many x-intercepts as there are factors. So because there's only one factor up here, one x-intercept. Then lastly, for the y-intercept, because the x value of the y-intercept is 0 by definition, what you're going to do to find the y-intercept, and it says it down here, you're going to take 0 and you're going to plug it into all of the x's in your function. Because I know x is going to be 0. To find the y, you're just going to plug it in. So if I do that, I would have 0 plus 7 divided by 0 minus 1. Because 3 times 0 is 0. So, again, it says down here, need a reminder, plug 0 into the function for all the x's. So 7 divided by -1, -7. I don't have it in these examples, but I may also ask you guys for the end behavior. The end behavior works exactly the same as it did last class. The horizontal asymptote is going to define your end behavior. It would be whatever the horizontal asymptote, it would approach that. If there is a horizontal asymptote, so the end behavior would be going towards 1/3. So it works the same way as first. Alright, so that's our first example. There's a lot of steps, there's a lot of memorizing the steps and all the different rules and things. So that's why this handout is made for you. You can also, I've had a lot of students in the past make flashcards, and they quiz themselves. They go through the process and go through the flashcards to remind what each of these rules would be, what you have to do, put them in order, in the correct order of how you do them. So that's another thing you guys can do to make sure you have the process down. Also practice. So we're going to do another one. Practice makes perfect. Alright, so the first thing I'm going to do is find the horizontal asymptote. That's always first. You're not going to do anything to this except find what the degrees are. What's the degree on the top? 2. The highest exponent is a 2 on the top. What's the highest exponent on the bottom? 1. So this is top heavy. The degree is larger on the top. It's top heavy. So what happens when it's top heavy? You don't have a horizontal asymptote at all. Okay? So you can write none or any if it does not exist. But if it's top heavy, you do not have a horizontal asymptote at all. Okay? Now, once you take care of that, the next thing you have to do, you cannot do anything else until you have factored your expression, if you can. In the first example, we couldn't, so we just moved on. But in this one, can I factor x squared plus 4x plus 3? Yes, that's a trinomial. We know how to factor those. So before you do anything else, we need to factor. Okay? Now, we have a process for the trinomial factoring with the x and all that with the factor by grouping. Have you guys noticed any patterns when we did the factor by grouping? When there's no coefficient in front of the x squared? What two numbers multiply to get 3 and add to get 4? 3 and 1. If you guys would normally do the process that we would do, right? You would do this, split down the middle, do I just end up with 3 and 1? You guys notice that? So is there a shortcut maybe I could use for this kind of scenario? If you know what those two numbers are, the 3 and the 1, you can stick them straight into the parentheses. That is only a shortcut that you can use to save time and space for these kinds of questions if the leading coefficient is a 1. If the number in front of the x squared is like a 2 or something other than a 1, you cannot use that shortcut. You will have to do the entire process all the way through. So just as a little tip for you guys, and you can feel free to do the entire process every time. If you don't mind spending a couple extra seconds to do that, and if you have space to do that, feel free. I'm just letting you guys know there is a shortcut that you can use just to save a little bit of time and space if you want to, but only if the leading coefficient is a 1. If you're really bad at knowing when to use shortcuts and when not to, don't do it. Don't do the shortcut. Do the process every time, because then you're going to mess up. If you see something like this one down here, can I use a shortcut for this one? No. So you guys, if you're really good at knowing when you can use a shortcut, when you can't, feel free. If you're not good at that, don't use a shortcut. Right? So I factor the top, and then the bottom can't be factored. I just have this. But once I've done that, what do you guys notice? Do you have something in common, top and bottom? So now I'm just working with x plus 3. So when I factor, I notice that I have the same factor top and bottom, so I cancel that out, and then all that's left is x plus 3 over 1, which I'm just going to write as x plus 3. Now, the entire rest of the question is going to be focused on this, x plus 3. You don't care about this right now, you don't care about this right now, we care about this. Okay? So now here we go. Where does the vertical asymptote come from? That was last lesson. Just in position-wise in general. We don't have h's and k's in these kinds of functions usually. Just in general, where do you look? Where do your eyes go? The denominator, they go down, right? Does this have a denominator? So what do you think that means? What do you think that means about the vertical asymptote? It's 0, x equals 0? I'll ask you again. Does this have a denominator? Yes. Okay, technically yes, it does. Are there any x's in the denominator? No. So if there are no x's to solve for, can you have any vertical asymptotes? No. If there are no factors, if there are no x's, if there's nothing to actually solve for in the denominator, you won't have a vertical asymptote, right? So you don't have to have a vertical asymptote every time. So just be careful with that. All right, now, what constitutes the presence of a hole? How do you know that you have a hole in your graph? If you canceled out a factor. So instead of a vertical asymptote, this one has a hole instead, because I took the factored form and I canceled out the x plus 1. So this one's actually going to have a hole. So the way that you guys find that is you're going to take whatever the factor was that you removed, that's why it's called a removable discontinuity. You're going to take that factor and you're going to set it equal to 0. So what factor did I cancel out? I'm going to take that and I'm going to set it equal to 0. What x value do I get from that? Okay. So remember, it's a point. So I need the whole point. So the x value that I'm excluding is negative 1. So we can all understand that negative 1 is not allowed. It's being excluded from the domain. That is being removed from the graph. But it is a point, so I not only need the x, I need the y. So once you guys find the x, to find the y value, you're going to take that x value and you're going to plug it back into the function. Not this one, not this one, this one. Everything is about this one, that's why I circled it. So if I know that the x value is negative 1, what would the y be when I plug that in? 2. So the entire point of discontinuity that I'm removing is the point negative 1, 2. Okay? Alright, now we can move on to the domain. So typically in our domain, we're going to jump over all of the discontinuities. One type of discontinuity is a vertical asymptote. Do we have a vertical asymptote? No. The other type of discontinuity is a hole. Do we have a hole? Yes, we do. What is the x value that we're going to be jumping over? Negative 1. So same structure as last time. You're going to be jumping over negative 1. Just the reason why we're jumping over it is because it's a hole instead of an asymptote this time. So whichever discontinuity you have, whether it's a vertical asymptote or a hole or both, you guys have to take those x values, and that's what you're removing from the domain. So those are the numbers you're going to jump over. That's right here. Okay? Don't worry about the range, just really cross that out. Okay. Now we're going to do the x-intercepts. Where did the x-intercepts come from? Where do you look? Where do your eyes go? The numerator. So what's the numerator of this guy? X plus 3. So I'm going to take x plus 3. I'm going to set equal to 0. What x value would I get? You have to write it as a point, so it would be negative 3, 0. There you go. You got your x-intercept. And then the y-intercept comes by taking an x value of 0. So that's the definition of a y-intercept. The x value is 0. And you're going to plug that into your function. If I plug 0 in, what do I get? 3. And then one more time, the end behavior, again, is defined by the horizontal asymptote. Because we don't have a horizontal asymptote, all we have is a hole. This would actually be a line, right? Y equals mx plus b. This graph would actually be a line with a hole in it, taking out that point. So the end behavior would be positive infinity or negative infinity on the left, positive infinity on the right. So again, end behavior, not going to be as much a focus on this lesson as it will next time, but you guys can see the end behavior more when you actually graph the picture, which we will do on the other side of the page. Not today, probably next week. Alright, let's try to fit in one more example for today. Let's look at this third one here. Alright, first things first, what do I find at the beginning? The horizontal asymptote. And the way I'm going to do that is by looking at the degrees. So it's the degree on the top. Degree on the bottom. Alright, it's bottom heavy. What is your horizontal asymptote when it's bottom heavy? Y equals 0. Please make sure you guys get in the habit of saying and writing a horizontal asymptote as an equation. So don't say horizontal asymptote is 0. It's y equals 0 because it's a line. Okay? Alright, next, before we can do anything else, what do I have to do? Factor and simplify. So take care of the horizontal asymptote and then go address anything that needs to happen with your function. So I can't factor x plus 1, so that's going to stay put. But I can factor x squared plus 3x plus 2, and I can use my shortcut. What two numbers multiply to get 2 that add to get 3? So if you want to do the full process, feel free, but you guys will find that your final answer is x plus 1, x plus 2, those two numbers that we just referred to. Why? They're both positive. Now what do you notice? I can cancel again. What does that leave me? 1 over. There will be a hole. That's a good catch there. But I'm going to have left, after I cancel out those factors, I have 1 over x plus 2. Why is this one 1 over x plus 2? Well, what's the difference between this one and what we saw? Because we had the same kind of situation happening in this one and then the other one. What's the difference? The remaining factors in the denominator, right? Over here, the remaining factors in the numerator. So this was the x plus 3 over 1. This one, when something cancels out of the numerator, you can't just make it go away, right? You still need to have something in the numerator as a placeholder. So if you have everything cancel out of the numerator, please make sure you leave something there. You're going to leave a 1 as a placeholder. So if everything disappears or cancels out of your numerator, put a 1 there as a placeholder and then leave whatever was left over in the denominator. It doesn't just become x plus 2. Because I was in the denominator, so let's leave 1 over x plus 2. Does everybody see the difference? Okay. Alright, let's take a look now that we have simplified that. Where do I find my vertical asymptote? Where do my eyes go? Where do I find the vertical asymptote? The bottom, the denominator, which I have this time. So to find the vertical asymptote, you're just going to take that, set equal to 0. What do I get? Negative, well, x equals negative 2. All you have to do, this actually looks just like what we saw last class. Remember, a reciprocal function has the 1 over everything. What was k? 0, that's why our horizontal asymptote is 0. H is negative 2. So actually this one's simplified into a reciprocal function. Coincidence. But all of our rules will still apply. Okay? Alright. right, was there a hole in my graph? Yes, there was, because I canceled out a factor. The factor I canceled was x plus 1, so I'm going to set that equal to 0. So what is the x value? This is a hole, so make sure we're going to write it as a point, because it's a point of discontinuity. So the x value I'm removing is -1, but that has to be corresponding with a y value. So I'm going to take this, I'm going to plug it in. 1 over 1. So 1. So the entire point of discontinuity or the hole is -1, 1. Yes, it could be a fraction. All right, now this one's interesting with the domain. We have two different types of discontinuities. We have the vertical asymptote and we have the hole. In this scenario, we have both of those. So there are two x's I'm going to remove from the domain, not just one. So when you guys are writing the domain, you guys can see I have right here, you can have multiple jumps. And the way that you're going to do that with multiple jumps is you're just going to jump over the first number and then immediately after that, jump over the second number, like this, okay? So on a number line, which one of these two x's would I run into first as I'm coming from the left? So I'm going to come from -infinity up to -2, and I'm going to jump over it. Now, if that was the only jump, I would write comma infinity, but that's not the only jump. What other number do I have to exclude from the domain? So from here, you're just going to go right into the next jump over -1. Those are the only two numbers I'm excluding? Then you can go on to infinity. So if you guys have multiple vertical asymptotes, or you have a vertical asymptote and a hole, or you have multiple vertical asymptotes and a hole, which would have 3 jumps, you just add them onto each other. You just go one after the other. So that's how you would write the domain if you have multiple jumps. And you can see I have it right here with x's, so you just plug in the numbers for the different x's. Okay? So remember that setup. And then lastly, our x-intercept. What is the numerator? Because the x-intercepts come from the numerator. 1, right? In order to find an x-intercept, don't I have to have an x to actually solve for? Do I have any x's in the numerator? So what do you think that means? What does that mean? There are none. If you don't have an x to solve for, you can't find an x-intercept, so there won't be any x-intercepts. They won't be crossing the x-axis. Is there anything else in the rest of the problem that justifies why we wouldn't cross the x-axis, why we wouldn't have an x-intercept? Why does that make sense with something else that we know about this? What's the horizontal asymptote? Where would that be? That's the x-axis, isn't it? Y equals 0 is the x-axis. Remember how we're usually not supposed to cross the horizontal asymptote? That's why we don't have an x-intercept. Okay? And then lastly, for our y-intercept, we're going to start with our 0, because we know that's how y-intercept is set up. So if x is equal to 0, to find the y value, I'm just going to plug that in, because I know y, or g of x, which stands for y, is equal to this expression here. So if I plug in 0, what do I get? 1/2. The very first thing you want to do is find the horizontal asymptote. You're not going to do anything to this except find the degree on the top and the degree on the bottom. So what's the degree? What's the highest exponent in the numerator? 2. What's the highest exponent in the denominator? 2. So the degrees are the same. Remember, when the degrees are the same, what you're going to do to find the horizontal asymptote, which is always y equals, remember it should be a line, so it's y equals, you're going to take the leading coefficients and write them as a fraction when the degrees are the same. So what's the leading coefficient up here? 2, and the leading coefficient here? What's 2 over 1? It's just 2. So our horizontal asymptote is just y equals 2. Okay, if the degrees are the same, top, bottom, you take the leading coefficients, which are going to be the numbers at the very front, if they're written in the standard form, which is usually you just take the leading coefficients and write them as fraction. Alright, vertical asymptote. What do I have to do in order to find that information? What do you do immediately after the horizontal asymptote stuff? Factor and simplify. So let's take a look at this one. So I was telling you guys about how with these trinomials, remember we usually do the x trick and then we split down the middle and do all that process. There's a shortcut you can use when it's just x squared at the front and there's no leading coefficient. Can I use that shortcut here? No, unfortunately, because if there's a number other than a 1 at the very, very front, if the leading coefficient is something other than 1, you guys can't use that little shortcut I taught you guys last time. So we're going to have to do the whole process for factoring. So I'm going to come down here, do our little x trick, our trinomial factoring. So we're going to multiply the first and last numbers. It's going to be -4, and middle number is 3. So what are two numbers that multiply to get -4 but add to get 3? Okay? Now, if I was using the shortcut, those would go straight into the parentheses, but I can't do the shortcut because I have a 2 in front. So what we're going to do is our process like we normally do. We're going to split the middle term. Go down the middle. Remember, you split the 3x apart and represent it with the 4 and the -1 with the x. Then we find the GCF on the left, GCF on the right. You guys should be familiar with this. We've been doing it all along. So what's the GCF on the left? 2x, leaving behind x plus 2. What's the GCF on the right? -1. And what's important about that is that when you pull out the -1 as a GCF, it's going to change the sign to get that x plus 2 to match the x plus 2 in the other one. That's how we know it was correct. Remember, that's our kind of self-check step within this process. And so the final factors are going to be 2x minus 1 and x plus 2. Again, we've been doing factoring basic for months now, so you guys should have this under your belt. You guys just need to take a little bit of extra time and space to do that one. And then how do I factor x squared minus 4? X plus 2x minus 2. Okay, so once I've factored, the next thing I want to do is see if there's anything I can cancel. They have an x plus 2 in common top bottoms. That means I have x minus 1 over x minus 2 left. I'm going to circle or star or highlight or something to make this stand out, because now the rest of the question is going to be based off of this form of the function. Okay? Alright, so now that I have that simplified form, where do you look for the vertical asymptote? Denominator. The denominator has the vertical asymptote. Remember, the vertical asymptote is a discontinuity. It is a value of x that's not allowed, and the reason why it's not allowed is because if you can't divide by 0. So we can't have a 0 in the denominator. That's how we get the vertical asymptote. So remember, to find the vertical asymptote, you look at the denominator, you pretend that it equals 0, you want to imagine that what shouldn't be happening is happening, and that's how you know which x value to exclude. So if I set that equal to 0, what x value would I get? 2. So that means that 2 is not allowed, because if you plug in 2, you get 0, which can't happen. You can't divide by 0. So our vertical asymptote is x equals 2. You just set everything in the denominator equal to 0, and that's how you get your vertical asymptote. Alright, how do you know if you have a hole in your graph? If you have a factor in that process that cancels out. Remember, a hole is a removable discontinuity. If you remove something by canceling it, that will create that hole. So what is it that I removed? X plus 2. So in order to find that as an x value, I'm going to take the factor that I removed and set equal to 0. So what's the x value I would get from that? It would be -2. But remember, a hole is a point. So not only do I have to find the x, I also have to find the y that is associated with that x. So once you find that the x is -2, to find the y value, you just plug it in. So I would have 2 times -2 minus 1 is -5. And then 2 minus 2 is -4. -5 divided by -4. Just going to leave it as a fraction. You can write as a decimal too, but I tend to like the fractions a lot better. But you can use your calculator to do it in your head, but it would become 5 over 4. Does that make sense? Okay. So those are our discontinuities. Now, once you have the 2 discontinuities, remember there are 2 different types. The vertical asymptote is one, and then the hole is the other. You could have one or the other or both. Once you have decided what the discontinuities are, now we're going to write the domain. Remember, you have to jump over the discontinuity. So what is a number that I'm going to jump over that I'm not going to have in my domain? 2, this is the vertical asymptote. What else? What other number is not allowed? -2, because I've removed it, right? This is not allowed because you can't divide by 0. So that's your non-removable discontinuity. This is removed from the domain because I canceled it out of the function, okay? So I have 2 numbers I'm going to jump over. We're going to use our double jump. You guys can see, you can see it on your page, but when you have multiple jumps, we just continue with the pattern like this. So remember, your domain is going to start at -infinity. Which number would I jump over first? Remember, I have to come kind of numerically on a number line. Which one of these 2 numbers would I encounter first? So I'm going to jump over -2, like this. And then from here, I'm immediately going to continue and do the jump pattern for the +2, which is going to be 2, like that, right? So I jump over -2, and then I go straight into jumping over +2, and then once I've done that double jump, I continue to +3. Just remember, any numbers that you need to exclude, you just have that breakup with the domain jumping over that number. Everybody good with that? Okay. X-intercepts. Where do the X-intercepts come from? The numerator this time. Alright, so you're going to take the numerator and set it equal to 0. So to find the X-intercept, I'm going to take 2x minus 1 and set equal to 0. What do I get? 1/2. So my X-intercept is 1/2 comma 0. Remember, an X-intercept is the X value comma 0. That's the definition of an X-intercept. And the Y-intercept is 0 comma some number, the Y value. We're not going to know what that is until we plug 0 in for X into our function. So to find the Y-intercept, I take 0 and I plug it into the function here for each of the X's. So that would be 0 minus 1 over 0 minus 2. Because 2 times 0 is 0. Yeah, so as a double negative becomes positive, so it would be 0 comma 1. And then I know I'm not asking for it here, but just a reminder again, the end behavior, just like the end behavior was interrupted by the horizontal asymptote last class, the same thing would work here. So if I asked you for the end behavior, you would just say on the left, y is approaching the horizontal asymptote, which is 2 in this scenario, and on the right, it would also be approaching the horizontal asymptote, which is 2. Alright, so end behavior works the same way, in case you see it. Alright, any questions on that before we move on? Alright, we're going to do the exact same thing. All the same steps that we just did on the previous page, except we're going to add the graph in. So you guys will need a calculator, either your own or share with somebody next to you, or just look at what they're doing with the person next to you. The graphs are going to be very sketch-like. You're not going to have a whole lot of points that you can graph, so it's going to be more of a sketch than it is going to be an accurate graph with a bunch of points. So, again, it's not our heavy emphasis, but you guys still need to know how to do it. So, let's go ahead and just do this part first, and then we'll save the graphing for last. So, up here, the very first thing you want to do is your horizontal asymptote. What do I analyze? What do I look for? Degrees. What is the degree in the numerator? And the degree in the denominator? 2. So they're both squared. The highest degree in the numerator and denominator are the same. So if they're the same, what do you guys have to do? Use the coefficients. So the coefficient on top is -2, the coefficient on bottom is 1. If you write that as a fraction, it's just -2 over 1 or -2. So that's our horizontal asymptote. Next, to find the vertical asymptote or anything beyond that, I would have to factor and simplify first. Okay, so let's take a look. In the numerator, monomials cannot be factored. So a monomial just is a monomial. And then the x minus 4, should remember how to factor the difference of perfect squares. I get x plus 2, x minus 2. Comes in. Stay awake. Follow along. Thank you, Jack. Alright. Can I cancel anything? Can anything cancel top and bottom? No. So I couldn't cancel anything, but it was still very good to have it in this format. Even though I can't cancel anything, I'm going to leave it in the factored form because it's going to be a lot easier to work with in factored form. Okay? So I'm going to leave it like this. Now, where do you find the vertical asymptote? Okay. How many factors do you see in the denominator? So how many vertical asymptotes do you think I'm going to have? I'm going to keep your head up. You will not fall asleep if your head is up. Alright, I'm going to have 2 vertical asymptotes. I'm going to set both of the factors equal to 0, and that's how I'm going to find my vertical asymptotes. So what's one of them? The first one will give you -2, the second one will give you +2. So I'm going to have 2 vertical asymptotes in my graph, at -2 and +2. Now, will I have a hole in my graph? No, because I didn't cancel anything. Didn't cancel anything, no holes. Alright, so the only discontinuities I have are 2 vertical asymptotes. So what are the numbers that I'm not allowed to have in my domain? -2 and 2. If it's a discontinuity, I cannot have those numbers in my domain. So when I write my domain, I'm going to jump over -2 and then +2. Very similar to the previous question. Double jump. There are situations, I seriously doubt you guys will encounter them, but there are situations where you can have 2 vertical asymptotes and a hole, in which case you would have 3 jumps. So, all right, next up are the x-intercepts. Where do those come from? The numerator. So if I take the numerator, if it's a monomial, and you set a monomial equal to 0, what do you get back every time? No. If I set a monomial equal to 0, what will x always equal? 0. It'll just be 0 every time. So the x-intercept is 0, 0. If the x-intercept is 0, 0, what's the y-intercept? Also 0, 0. All right. So once I have all this information, now we're going to graph this. So we're going to start by graphing the asymptote. So I know I have a horizontal at -2. I know I have a vertical at -2. And positive 2. Yes, asymptotes are always dotted. Because they're not actually part of your graph, they're just boundaries. They're exclusions. The next thing you're going to do is graph any points that you already have found. So that would include the x-intercept and the y-intercept, which are the same point for us. So I'm going to graph the point at the origin, 0, 0 for the x-intercept and y-intercept at the same time. Now, you guys, just like last time, you guys are going to use your calculator to get the rest of the picture. So in your calculator, and you have to be very careful. You have to be very careful just like you did last time. When you're typing it into the calculator, use this form. Use the form that was printed. But remember, you still need to use the double parentheses setup. So do parentheses around the entire fraction, and then do another set of parentheses around the denominator itself. If you don't have a calculator, you can just look over the shoulder of somebody next to you if they have one. So you would type parentheses, -2x squared divided by parentheses x squared minus 4 parentheses parentheses. Okay, so make sure that you have the entire fraction in parentheses and the denominator in a separate set of parentheses just to make sure that the calculator doesn't get confused. And then once you have that all set up, hit second graph. Again, we're going to go look through our table of values. Now, when you guys are there, or as you guys are getting there, remember that my expectation for you guys to graph, I am not expecting you to graph any crazy decimals beyond a 0.5. So if you see a decimal that is other than 0.5, I do not expect you to graph that. So I only expect you to graph whole numbers and decimals that are at 0.5. So when you guys are looking through that table of values, do you see any points that we can graph? You type 2. That is not a point on our graph. That is also not a point on our graph.
2, 0.
No, 2, 0 is the asymptote. You gotta be careful. Sometimes the calculator, again, the calculator is very finicky when it comes to the picture and the points, so calculator may not recognize the asymptotes or may not graph them, but you guys need to be aware that they are there. So if we try to say 2, 0, you know that's not going to happen because there's no asymptote there. Yeah, there's no 0.5. So the point I'm trying to get across is that as you guys are going through that list of values, you're going to get points that are not allowed to be on the graph, or you're not going to find decimals that can't be graphed. So essentially for this question, the only point that we can actually graph is this one. There are no other points that are nice and easy to graph. Okay? So for when you guys are looking at these and you're trying to graph these, instead of using the table of values, go and check there first. But if you can't find any nice points, you guys are just going to look at the picture instead. Do not, in your calculator, look at the picture from what we were doing last class. I looked at the quiz really quick and I saw somebody did not listen to me, and they graphed something crazy that looked like this or something. And I specifically said not to do that because your graphing calculator does not know how to graph these very well. They just have like this weird shape that look like that, which is what your graphing calculator would show you if you look at the picture, but that's not what it should look like because your calculator doesn't know how to graph them. However, it does a little bit, tiny bit, better job with these graphs. So everybody with your calculator, instead of hitting second graph, hit regular, just graph, so you can see the picture. Your calculator will do a little bit better, still not going to be perfect, but a little bit better. Again, my expectation is just a sketch, so when you guys look at your calculator, you should see a swoop over here, somewhere-ish, a swoop over here, in this corner, and then a parabola right there. That's what it should look like. And of course, when you're at home, you can use Desmos too. I'm sure Desmos is even better than your handheld calculator. But this is the general idea. Again, it's a very approximate graph because I don't know any of the exact points here. So I just draw a swoop here, a swoop here. I make sure that my parabola shape actually touches the origin because that's the one point that I actually have. But any of the other points, I don't know. So it's just a sketch. Okay? So you can use your graphing calculator to get a general idea of where the parts would be in the graph, and then just draw me a sketch. You can always compare to Desmos as well to get a better idea. But again, it's still not going to be perfect in your calculator. Just getting an idea. So I just want to emphasize this one more time, your main emphasis should be on the information you get over here. You are only using your calculator for like 10 seconds to get a very brief glance of what the graph should look like. Other than that, just getting a general idea of what the graph looks like, you should not be depending on your calculator. Okay? Alright, questions on that one before we try the next one? Let's give this one a shot. I'll let you guys do a lot of this by yourself. Raise your hand if you think you know what you do first. Okay? So what are they? Okay? How is that significant? You to use your hand out or flip back. It's bottom heavy, right? Bottom heavy means y equals 0. What does top heavy mean? If the degree is big, I call it bottom heavy. If the degree is bigger on the bottom, then it's y equals 0. If the degree is higher on the top, if it's top heavy, then the horizontal asymptote does not exist at all. Okay? Who knows what to do next? Okay? How? Bottom one is 0? Nope. How? No. Nope. Nope. Come on, guys. Yes, that's what I'm asking.
I'll take the x out, right?
So what does that give you?
X minus 4.
That's the only factor?
No, x minus 4 and x. No.
No. There you go.
Oh.
It's very simple GCF. Very simple GCF. All you do is take the x out, and then you have the x minus 4 left over. Now what? Okay.
Oh, now you solve.
Ladder. Okay. Now what? Let's save that for later. What am I trying to find next? The vertical asymptote. Say again? So what equals 0? Because it's where? Okay. So
X equals 4.
would be what?
Would be your vertical.
Okay. Next. Okay, how do you know if you have one? Okay, did I have one? Okay. So x is canceled out. So then how do you actually use that to find the whole? So what equals 0? Okay. So the whole is just 0. The x is 0. Okay. So what'd you get? Plug it in where? Where?
Oh, negative 4. You get negative 4.
Nope. Negative 1/4. You guys are tripping up on the simple stuff. You just plug it in for x. So the value where that's being excluded with the removable discontinuity is 0, comma negative 1/4, that entire point. Alright, once I have all of this information, what would I do next? Okay. Okay. Two discontinuities, so I jump twice. Now what? What comes next? Okay, where do you look for those? You look in the numerator. What's in the numerator? Are there any x's to solve for? So what do you think that means?
0.
Say again? None. There are none. If there is no x, you can't say x equals 0, because there is no x to solve for. So there are none. What's next? And last before we graph? How do you find the y-intercept? We know by definition the x is a 0, right? And then find the y, you plug it in. What do you get when you plug in 0? Interesting. How is this interesting? It's the same as the whole. Which one do you think is going to override the other? The whole is going to override the y-intercept. Okay? So if you get this kind of rare scenario where the whole and the y-intercept happen to be the same points, the whole is going to swallow up the y-intercept. So it would actually go away. So be on the lookout for that. Could happen. But yes. Because the whole is going to erase or cancel out the y-intercept there. Alright, so now we're going to graph. So I'm going to take my marker or pen or whatever you guys are using. I have my horizontal asymptote at 0. With the axis right here, I have 1, 2, 3, 4 right here. Then I also have one other thing that I need to draw. I graphed the horizontal asymptote. I graphed the vertical asymptote. What else do you think I might have to graph here? The whole. We don't have a y-intercept, remember? We're going to graph the whole. We don't have an x-intercept because the asymptote is the x-axis, so I can't cross it. But I am going to graph the whole. Now, because it's so small, it's just that point that you're excluding. It's very hard to graph that. So, especially since it's a fraction. So the best thing that you guys can really do is just draw like an open circle right here about where the whole would be. So like around 0, negative 1/4, around here. So just draw like an open circle to represent the whole in our graph. It's like a black hole. Okay? Now the next thing you're going to do is again try to find some points in your calculator. No promises that you will find any. And if you don't, you can just use the picture to give you a guidance on what it would look like, but your calculator may give you some. So let's take a look. So go ahead and put this into your calculator. Remember this one right here? This guy? So x divided by, parentheses, x divided by, and then another set of parentheses around the denominator. And make sure you close both sets of parentheses. Then we're going to hit second graph to look for some points first. You're going to see a couple nice ones. Okay, so there's a 2, negative 0.5 right here. So that's one that we can graph. Is there another one? 3, negative 1. Any more? 5, 1. I think there should be one more that's relatively okay. 6, and then 0.5. So I have these points. They're going to give us a good idea. So if you guys look at how our graph ended up after we simplified, doesn't this look familiar? Yeah. This is like the kind of graphs we were doing on day 2, where we had 1 over and then the binomial in the denominator, right, with the h's and k's. So once it simplifies to become a reciprocal function, your graph is going to look like a reciprocal function, like we saw last class, or not last class, but the day 2. The only difference is that we have this hole here. So if you guys were to now hit graph in your calculator to see a picture, your calculator will not have an empty hole. Again, your calculator is very imperfect. It will not be able to graph discontinuities very well. So your graph is going to look like you just go woo right through there. So that's why you guys need to be extra careful when you're using your calculator. It's going to show you in general what the graph looks like, so you can see that hyperbola shape with the curves. But when you guys are actually graphing it, I need you to pick up your pencil. Go on the other side of the hole. Do not go through it. You need to leave a gap. And then you have the curve over here. Okay. So again, your calculator is a guide. You have to be really, really careful. Don't trust it too much. It's going to give you a general shape. But again, if you are depending on this information, the analysis that we did beforehand, make sure you have all the little details in place, because your calculator will not show you all the little details every time. Okay, so I have that hole that needs to be open. Do not graph through it. All right, any questions about that one? All right, let's try. We'll see where we get after we try this next one. Actually, I'm going to let you guys try it by yourself. Try this next one by yourself, please. Here we go. What do you guys get for the horizontal asymptote for this one? None. Why is it none? It's top heavy. The degree is higher on top, so no horizontal asymptote. Alright, before you do anything else, after you take care of the horizontal asymptote, what's the very next thing that you do? Factor and simplify. What would the factored representation of the top be? Can I use that shortcut for this one?
Yes.
Yes, you can. Because the leading coefficient is a 1. If there's anything in front of the x squared, like a 2 or 3 or something other than 1, you can't use the shortcut. But if it's just x squared by itself, then you can. Alright, then what? So what does that leave you with? Everything for the remainder of the question is going to be focused on that form of the equation. Okay? Alright, what would the vertical asymptote be? Nope. It would be none. Where does the vertical asymptote usually come from? Does this have a denominator? No, it does not. Well, the denominator is 1, but there's no x in the denominator. Okay? So there's no more denominator, no more vertical asymptote. Is there a hole in this graph? Yes, there is, because I canceled a factor. The factor I canceled was x plus 2, so then the x value, after you set that equal to 0, would be negative 2, right? And then because it's a point, I need to find the y value, so I take the x and I plug it into the only equation I have, which is this one. I plug that in, I get 1. So I'm going to have a hole at negative 2, 1. Then I'm going to write the domain. The domain is going to jump over the discontinuities. The only options we have for discontinuities are the vertical asymptote and the hole. I don't have a vertical asymptote, so the only number I'm going to jump over in the domain is negative 2. So I have a single jump. The x-intercept comes from everything we're talking about is coming from the simplified form. I'm talking about specifically where? The numerator. So if you need to write it like that, that's fine. Again, we didn't really have a denominator, but the numerator is x plus 3. So it's negative 3, 0, because you have to set the factor equal to 0 to actually solve for x. You have to solve for x. So I get negative 3, 0, and then for the y-intercept, 0, 3, because I plug in 0 for x, using the definition of a y-intercept, I get 0, 3. Next up is actually graphing it. Okay, so we're going to take everything that we know. I do not have a horizontal asymptote. I do not have a vertical asymptote, so I have no dotted lines. But I do have a hole at negative 2, 1. So I'm going to draw an empty circle right there. I also know that I have an x-intercept at negative 3 and a y-intercept at 3. Now this is going to be a very easy graph to draw, because what kind of shape does something as simple as y equals x plus 3 make? What kind of graph will that make?
You made, right?
Y equals x plus 3. It's a line. It's a line. It's a very simple line. So it has a slope of 1 with a y-intercept of 3. It's going to, when you guys simplify, it boils down to a graph format you guys should be more familiar with, like our reciprocal function we saw a second ago, our line that we see here. Sometimes they're a lot more complicated, but oftentimes they will boil down to something that you can actually graph a little bit better. So you're going to graph this lift your pencil so you, oops, do not actually go through the point, but I have a line, or the hole, I have a line with the hole in the middle. That's where your graph will look like. Okay? And again, if you guys are not sure about that, this saves you time recognizing the format of the equation and what kind of picture you would get from that, just intellectually, kind of, or intuitively seeing that. If you're not able to do that and you have to use your table of values, you can still do that. If you type in or your original equation over here into your calculator, use the second graph for the table of values, or just hit regular graph to see a visualization of the final product. You'll see it there too. It just saves a little bit of time if you guys are thinking about the shape of your graph from the simplified form. Okay? Is there any questions about anything that we've done so far? Alright, I'm going to leave that third one